Okay, so today we're going to talk about the application layer, the top layer in our Internet protocol stack. And we're going to start with talking about some principles of network applications, and then jump into some specific application layer protocols that are super common, HTTP, FTP, and the protocols involved with email, SMTP, POP3, and IMAP. As we start off, can you guys think of what are some network applications that you can think of just off the top of your head, maybe besides the three that I just said? An application that runs over the network that would therefore require being implemented at the application layer. What network applications do you use and enjoy? Gmail, okay, so that's primarily HTTP based, but it's going to involve some other protocols as well, like the email protocols. What else you got? Can you think of another program on your computer that's a network-based program? That's basically going to be an application layer. Dropbox definitely counts. They got an application layer protocol that they use to communicate all those file synchronization things about. Joey, it's all on you now. Anything?
Chrome? Same one? Never did.
It's a browser.
Yeah, it's a browser, and it's going to implement the HTTP protocol to communicate. That's its primary form. You can think about, there's lots of other stuff that you would use on a computer, like instant messaging, any kind of network streaming based apps. If you're streaming videos, those are application layer protocols. Voice over IP, those kinds of things are some network applications. Here's a list of them for your betterment. Nothing really shocking here. Okay, so how do we create a network app? A network app, really the goal is that we want to run this application on different end systems. So it's going to run on different hosts, but work over the network. It's going to involve communicating over the network. The kind of most common, most popular network application is the web. And the web is implemented as web clients, which are browsers, your browser like Chrome, Firefox, Safari, and web servers that are running software that communicates with those browsers and returns pages and resources that you want. Notice that in this scenario, and this is what we're going to see, there is no need to write software for the network core. All of the logic that's involved in the application is implemented at the endpoints. It's on the end systems. Because the internet is designed in this way, it allows for rapid application development and propagation. You can make a new network app and everybody can use it on the existing network core infrastructure. Right? So you don't have to buy a new router, or the backbone networks don't have to buy new routers in order for a new instant messaging software to work, because they use the same core. It's the higher level that's different, but it's the same network link and transport layer as in previous scenarios. So as we said last time, an application layer protocol works on an end-to-end basis. Remember that end-to-end versus point-to-point. So because of that, end systems are communicating with each other. So that is section 2.1. No, we're continuing on in section 2.1. All right. So these are the kind of three, really two and a hybrid types of application architectures. We mentioned these already in this class. One is the client-server architecture. So this is really popular today in the sense of, in the context of data centers and cloud computing, where you've got these super powerful servers or farms of servers, server farms that are doing lots of, they're always on and they're providing a service to the clients who always will connect to those servers. The other approach is a peer-to-peer architecture where kind of everybody's on equal ground and there's not this super powerful server that everybody connects to. Everybody can connect how they want to among themselves. We can, of course, combine these two things together in a hybrid approach and do a little bit of client-server and a little bit of peer-to-peer. The idea of doing that, like doing any hybrid approach, is you kind of get the strengths of both and maybe they cover each other's weaknesses. So let's talk a little bit about each one.
What was the last one?
Hybrid. So in a client-server architecture, we've got servers that are always on. They have a permanent IP address, and there may even be server farms where you've got lots of servers together that for redundancy and higher availability. They make it easier to scale. Clients communicate with the server. They might just be intermittently connected, right? Their IP addresses might change. They don't directly communicate with each other. In a client-server architecture, if clients are communicating, they're going through the server. So all the way back to the server, back to the other client. Implementing client-server architectures is a big deal because client-server architecture is such a dominant architecture. It's the way a lot of protocols are structured because it's a lot easier to manage and think about. If you think about Google, I've got some older numbers here, but they have these data centers that contain server farms. They're super expensive, and they spend a lot of money building them and a lot of money powering them. The power costs here are really immense.
Do you know where they release where some of those are at?
Yeah, I think they're throughout the country. I'm sure we could find it on YouTube. They are a little bit secretive about some of the processes that go on inside because they have spent a lot of money optimizing that stuff, and they want to get high computation efficiency for the power that they have to pump in there, right? Because they have to spend a lot of power on air conditioning. I think I read an article a while back that was talking about they were considering putting these on floating platforms and using the water in the ocean to help cool.
They already do that on a lot of them, like an Apple too, but they build them around water.
No, okay, good call. So they're trying to find ways to save money, and usually that money is about heat and how to get rid of the heat. So that's one approach is client-server. Second approach, peer-to-peer. In a pure peer-to-peer architecture, there is no server. There is direct communication between arbitrary end systems. Anybody can kind of be a client and a server and talk to anybody else. Because of this, the peers are intermittently connected. Their IP addresses may change. This is nice because it's highly scalable, right? You can imagine if you've got 1,000 users in a client-server system, they're still going to have to connect to that one server because it's the guy that has the resources that knows how to do the job. If you've got 1,000 systems in a peer-to-peer fashion, then we can distribute that out and have lots of people talking to other people as long as they all have the resources. And an example of this is something like BitTorrent, where everybody is sharing a file and splitting it up, and that kind of lowers the work that everybody has to do by splitting it up. It's really about dividing and conquering. The problem here is that it's difficult to manage, right? You've got to do a lot more work to manage all this because everything is everywhere, and you can't just change the configuration on a server to change the system. As an example of a hybrid client-server and peer-to-peer, Skype is one example of that where you guys have used Skype. It's a way to video chat or audio chat over the internet. They have a centralized server that's used for initializing a connection with a remote party. But then once you guys are connected, you're connected over in a peer-to-peer fashion just directly through each other. You don't have to use the server anymore. So that kind of uses both to get the best of both worlds and cover the weaknesses. All right, let's talk about processes. Processes are just programs running on a computer, on a host in this case, a network-connected device. We talk a lot about this in the operating systems class, but a process is really just a special name for a program running on a computer. At the application layer, the main goal is just to communicate from one process to another process. And when we think about those two processes talking to each other, we have to ask some questions. Where are they? All right? It's possible that the two processes could be on the same host. If two processes are on the same computer, they can talk to each other through systems like inter-process communication, which is something provided by the operating system. Right? That makes sense that if you're two processes on the same computer, should be able to talk to each other fairly easily through mechanisms provided by the OS. If they're on different hosts, however, we're going to need to use a network to exchange messages. It turns out we can actually use a network-based system on the same computer if we want, and then the network message doesn't even have to leave the computer and go out on a real network. It can just be handled by the local system. All right. In most scenarios, pretty much all scenarios, there is this idea of a client process and a server process, even in peer-to-peer scenarios, in that these are more like kind of roles. A client is the process that initiates the communication, and the server is the one that's kind of waiting to be contacted. So you can imagine, even in a peer-to-peer environment like Skype, when you're making a call, to your mom, which I know you guys do a lot, when you're initiating the call, you're the client in that scenario, in that role. You have the client role, and your mom has the server role. Right. This chapter talks a lot about sockets. It's a really important idea in this context of communication, network communication. And a socket is really just an endpoint. An endpoint for communication. The socket is an API, a programming interface that's been around a long time and that's very common to kind of abstract away the complexities of communicating between two processes. The book has a nice analogy saying that a process is like, the socket system is like doors. A socket is the door. The transport layer, which is the layer underneath the application layer, is the hallway. Right? So the transport layer actually gets the thing, whether that's a person or I don't know, whatever it is we're throwing down the hall to the other doorway. The transport layer is the mechanism that moves that. So the sending process is going to shove the message out the door. The receiving process relies on the transport layer to get it to that door. And then that other socket, the other endpoint for communication, is going to accept and receive the message and do what it needs to do to pass it, to implement the application layer. So a socket is just the endpoint for communication. It's like a door. Another way to think about it is that it's like a faucet, where we have the faucet is the endpoint, that's like the socket, and the transport layer is the pipe that's actually pushing the water around, or holding the water as it moves. The water in this case is like the message. Okay. So here's a more network view of this system. So we have two hosts which are running processes that are communicating with each other. Those are hosts communicating, processes communicating over this application layer. The means by which they communicate, right, the endpoints, is this abstraction called a socket. The socket is going to sit on top of a transport layer, which may be TCP, and TCP has lots of complexities. These complexities are normally implemented by the operating system. TCP is going to make sure that that message gets pushed across the internet. The other computers is going to implement the transport layer to extract your message, send it to its socket, which passes it up to the process. So the socket is just an endpoint for communicating between processes, even processes on remote machines. Okay, so one question we would ask then is, how can we identify a process? How can we identify a process? We know that in networks, an IP address is really is really important, and so that's probably going to be something we need. But is an IP address enough? That's the question. If we have the IP address of a process and the IP address of another process, can those two processes communicate over the internet with IP addresses? As we think about this, if you want to see what a process is and what processes are running on your system, you can run these command line programs, task lists in Windows, or PS or top in Mac or Linux. If you want to open up a console and type in these messages, you can see all the processes that are running on your system. In Windows, you can do the process manager. What's that thing called?
Windows Task Manager.
Windows Task Manager, and get a graphical version of that. So when you look at that, what we're saying is every process has to have a unique identifier in order to communicate with another process. Is an IP address enough? The answer is no. We need an IP address. The IP address is really just the address of a host. The address of a host. But a host may have lots of processes running on it. Okay? So how does a message know, I want to go to this process on this host? So we need another bit of information, that is another piece of information, so that those two processes can communicate, so they can send a message to the right process on the right host. What's that other piece of information that hosts will need to identify each other? No, not MAC address at this level. Port number. You guys heard of ports, right? When you think about ports, really all a port is a way to uniquely identify a process on a system. So when you take the IP address and the port number together, you get a unique ID for a process, basically, for communication purposes over remote systems. So, for example, if you're running an HTTP server, a web server, it runs on port 80, and that's well known. So browsers, when they want to do HTTP, get HTTP files, they're going to send messages to the IP address of the server and the port number associated with HTTP, which is 80. So we have to send the IP address and the port number to get that. And all the well-known services have a port number that's associated with them, so that you can address the right process on that computer. Does that make sense? So a port number and IP address are really just an identifier for a process on a computer. What is it that the application layer protocol defines? All right, it defines these four things. And on the right, I found this nice diagram that kind of gives you the idea of how encapsulation works. But what we're really talking about is what is in this application layer message, this very top message, before it gets sent down and broken apart and sent across the network through the process of encapsulation. First, we have a message type. This is something like a request or a response, the general type for the message. The protocol will also have to define the syntax. That is, what are the fields, the subcomponents of the message? How are they delineated? How do you separate the fields? How do you tell what's what? Thirdly, message semantics. Message semantics is the meaning of the information in the fields. What is it that's in each spot of the structure of the packet? So the syntax describes the structure and the semantics describes the meaning. And fourthly, the rules. So the protocol defines not only the types, the syntax and semantics of messages, but the rules associated with sending messages. When and how processes respond to messages. Okay, so what do we do when I get this message? I do this next. That's defined in the application layer protocol. I think this to the right gives you a good picture of encapsulation, in the sense that if we have this big message we want to send, the transport layer, like TCP or UDP, is going to possibly break that up into chunks. And then for each chunk, it's going to add on its own header information. The network layer IP is going to add on its own information, its own header. And then the data link layer is going to add on its own information before it's sent across the LAN physically. On the opposite side, it'll have to do this in reverse, and it'll get this whole big packet and unencapsulate it, decapsulate it. Questions about application layer protocols and the stuff we talked about up to this point? Okay, so a couple of application layer protocol issues we want to, or protocols themselves. Some protocols are in the public domain, meaning that the protocols themselves are defined in an open way. Everybody can see exactly how this protocol is supposed to be implemented, And if you can follow the rules that are in the document that defines it, then you can write a program that implements that protocol. These are examples of public domain protocols. So HTTP, these are actually all defined in documents called Request for Comment, RFC. You can look up RFCs online, and those are very, very technical definitions of the protocol. So if you wanted to write your own web browser, you could go out, read the HTTP protocol, and implement code that would follow that protocol to the T. And if you did that, then you could communicate with any web server because you're following the same standard for exchanging messages and message format, semantics, message order, all those things we just talked about. Make sense? Other protocols are proprietary, meaning somebody developed them and they're not telling the inner workings of it, right? So Skype uses some proprietary protocols, and they don't want to interoperate with other people. They want you to use their stuff on their network. They're not going to let anybody else.
Skype's free though. So.
Right, it's free, but you couldn't create another program that could work in the Skype network. You couldn't make a phone call from a non-Skype program to Skype. I understand why would you want to do that? Because it's free, but they're in control, and they do charge for some things, right? Like overseas, landline, calls to landlines. I think you have to pay money for that. All right, let's talk about some of the services that are provided by the transport layer. All right, so as we're designing our application layer protocol, we're thinking, really, when I'm working on an application layer protocol, I have to understand the level underneath me. That's going to be true at every level. All right, what's going on underneath me, and what kind of properties do I need the transport layer to provide? Because that's really what I'm working with as an application layer. I'm working with the transport layer and sending messages across it. All right, so one property is data loss. Some transport layers would make sure that that there's no data loss at all. Others might allow for some data loss, not prevent data loss, not recover from data loss. So the questions we're asking ourselves as an application layer designer is, does my app require 100% reliable data transfer, or can I get away with some loss of packets? Can you think of a scenario where it would be okay to lose some packets?
Skype.
Like Skype, all right? So if we drop a packet that's in a voice call or a video call, the screen may look a little jumbled, a little pixelated, or we may skip a blip of sound, but we can still communicate, right? Can you think of a scenario where you have to have reliable data transfer? This is an easy one. There's lots of stuff that you will not accept. Corrupted data, missing data. Email, right? Yeah, I mean, you don't want to get an email that has like the whole middle portion missing because that packet was dropped. It's kind of important that it's 100% reliable. So that's data loss. Another question is timing. Does our application require low delay to be effective? Can you think of a scenario where having a low delay is important to the application really functioning at all?
Like a low delay, just mean like.
I get the time between sending a packet and receiving a packet, that there's a limited amount of time where that where it's not going to grow really, really large delays.
I don't really understand the question you're asking.
Okay. What I'm saying is, it's just like we talked about before, any kind of audio app where you have a real-time chat between two people, that application layer and the transport layer underneath it is going to have to make sure to get the packets there in 500 milliseconds, say, sometime. Even if you get the packet there 3 minutes later, it's completely worthless because we've already skipped that point of the conversation. You see what I'm saying? So those kinds of apps, like and even games, are like this too, right? Lag in games. If you can't get the data there in this amount of time, then you shouldn't worry about it at all, right? Whereas if you're downloading a file from just a music file, say from iTunes, it's okay if one packet takes a lot longer than the rest, as long as you get it all. You know, those timing requirements are softer. Okay. Another consideration is throughput. Is there some minimum amount of throughput that you have to be effective? What is throughput again?
Amount of time it takes to have it or something.
Well, throughput is a rate, but it's bits per second. So that's related to time. How long, how fast are you getting something through? Okay, your answer was really close, but I want to be clear on this. So throughput is a bandwidth. Can you think of an app that has to have a certain amount of bandwidth to be effective?
YouTube.
YouTube. Okay, and you say that because if you can't download as much as you're going to watch in a second or in that period of time, it's painful to watch, and that's why you have to buffer it, right? So if we buffer it, even if it's a slower connection, we're enough ahead that we'll catch up, right? Again, any multimedia, streaming audio, video, real time is going to have this kind of requirement, where if you can't give it, you know, one kilobit per second, then it's just not going to work. It's not going to be an effective use of that app, because you're going to never be able to deliver the packets that you need to have this real-time exchange of information. Whether that's audio information, video information, games might be this way as well. Other applications are more elastic in that requirement, like we mentioned, email or web browsing. If you're on a really slow connection, you can still browse the web, you just have to wait for it all to download. If you're on a really slow connection, you may not be able to do Skype at all, right? It's just not going to work. That's the thing. And the last one is security. Sometimes you need to ensure that there is encryption, that your information is hidden, that the information is true, that there's a data integrity part of security, that you can make sure that you got the information that the person sent and it wasn't tampered with in between. All right, so these are 4 services that transport layers may or may not provide, and you're going to have to make sure as an application layer designer that you're using a transport layer that provides the services that you need. All right, so if we think about some typical application layer protocols and think about, for each of these 3 that we've talked about, taking off security, do we need these 3 transport layer services? What about for file transfer? Do we need the no data loss, reliability?
Yeah.
Yes.
Yes. Is it time sensitive? Not really. It's more elastic, right? And throughput, do we have throughput requirements for the file transfer in order to be effective? Not really. If it's slow and then fast and slow and then fast, we'll eventually get the file and it'll be okay. You see, whereas if it was slow and fast in a like real-time audio video, that would be unacceptable. The app would not work. Email, how about email? Data loss?
Yes.
We need to be, yeah. Is it time sensitive? Not really. Throughput? No. Web is the same thing, right? We need all the data, but there's not hard time or throughput requirements. Real-time audio video is different. Can we allow for data loss? Yeah, we said we can. Is it time sensitive? Yes. And do we have minimum throughput requirements? Yes. What about if we're just downloading audio video? Is that, so it's not real time, but it's pre-recorded, as it were. Is that,
You can't have data loss.
so we probably don't want to have data loss. Maybe we could support a little bit, but prefer not. Is it time sensitive? I mean, it depends. If we can do some buffering, then we can kind of take both of these. We can mitigate them at least. Interactive games, how about that? Can we have data loss?
A little bit.
Maybe you can have a little bit. Think about if you lose a packet, then you go from here to here, and we're never in the middle, which would be annoying to people who are maybe playing against you. But there's some loss tolerance, is what I'm saying. It is time sensitive, right? Lag, and there are throughput requirements. Instant messaging, probably want no loss there. It may or may not be time sensitive. Probably not, and pretty elastic throughput
When you
requirements.
time sensitive, since it's instant messaging, it's kind of like in the name.
If it's not instant, it's false advertising.
Yeah, I don't know. I mean, it depends on, there is this kind of acceptable level of, is a late packet worth anything? And if it's the difference between, like if it's a second, maybe a second or less, then you're okay if your whole message gets delayed a second. But once the message has been sent, there's no reason to, send it again because they would have already received part of the message. So that's kind of, since you're dealing with a human being, the requirements are more elastic. Because it's a little bit real time in the sense of
But
that
does
a
it
human
send a
being.
message if it has a drop packet, like, or will it like retry to send it? Because on most messages, if you leave out a word or two, it can change the whole message.
Right. So if we send it and we send one message, but it's broken up into like 3 sub messages.
Yeah.
Let's say we get 2 of the 3 through. Should we try to get the third one through? Well, it kind of depends. Like if it's just been like a millisecond since we sent it, we could get it there before the person has read the whole message. But if it's been 5 minutes, there's no point. That's kind of what I mean.
So what do they do to make that not happen? Like, do they just get their application not to display the message until all packets are received, or?
Or you might have a kind of a buffer where you're accumulating packets, and once you've emptied the buffer and displayed the message, then you can't change it. You'll ignore any other packets that come in with that same message of that same message group. Here's what the author had in his table of kind of the answers to these questions, and we basically already went through all that, but if you're interested in the details, you can look into that and see. There are 2 internet transport protocols. So these are the 2 real-life protocols that are in use that are options for application layer protocol designers. They're called TCP and UDP, and we're going to talk about them a whole lot more in the next chapter. But just as an introduction today, we want to see how we use TCP and UDP, just to kind of get an introduction to it so we can see how we use it to implement application layer protocols. TCP has these characteristics. It's connection oriented. That means that we're setting up a connection between client and server processes. That means that there is some overhead. It takes some time to set that up initially. TCP is a reliable service, meaning it'll make sure the data gets through. It will resend packets if they're lost, and it's going to make sure that they're not lost. Well, it'll make sure that if they're lost, it recovers from that lost packet or corrupted packet or duplicate packet. TCP provides flow control. Flow control is about making sure that the receiver is not overwhelmed by a really fast sender. All right, so you can imagine if you have a sender who's sending data super fast, like 100 megs per second, but the receiver can really only take in and process 10 megs per second, it's not going to take very long for the receiver to be overwhelmed and just begin dropping all the data that's sending. So flow control makes sure that the receiver is not overwhelmed. It'll slow down the sender, basically. Congestion control is the last thing that's important, an important property of TCP. Congestion control throttles the sender, watch it here, when the network is overloaded. All right, so these 2 things are different, flow control and congestion control, and the difference is in why and where the congestion is happening. All right, flow control is slowing down the sender because the receiver can't receive that fast. Congestion control is slowing down the sender because the network can't deliver the packets that fast. That the network is experiencing congestion, so the sender needs to slow down because his packets are being lost in the network. The receiver might have been able to keep up, but he wasn't getting them because the network was slow. So they're really 2 different things, and they're solved in 2 different, with different procedures. All right, questions on TCP up to this point on these 4 properties? Okay, do note what's not here. Do you see timing on here? Negative. No timing guarantees. Do you see throughput guarantees on here? Nope. And do you see security on here? Right? Several of those things we talked about before, not provided by TCP. So what are we going to do? Well, let's come back to that. Notice UDP. UDP is connectionless as opposed to TCP, meaning you don't have to set up a connection ahead of time. When you want to start sending, you just send. Just send away. It is unreliable, meaning when you send a packet, there are no guarantees that it will actually get there or be uncorrupted or be unduplicated. Thirdly, there is no flow control. So if you blast away at the sender, you may overwhelm the receiver. And UDP is not going to help you with that. It's just going to let you send away as fast as you want. And fourthly, there's no congestion control either. So there is, it's possible that you could overwhelm the network by sending a bunch of UDP packets, and the network, the sender is not going to slow himself down because the network is congested. So when you look at this, you may think UDP is junk. Why even have that around? Can you think of a reason why we should even bother with UDP, since it seems so bad? It provides so few services.
Faster.
Faster. That's a really good point. If you think about the stuff that's on here, it takes time to set up a connection, right? You gotta do some work ahead of time. It's kind of like setting up a circuit. Right? You've got some initial overhead. UDP, you don't have to waste that time. You can just send when you're ready. Another thing is reliability. Yes, reliability is nice, but it's not free. You know, there's always a trade-off. How is it that this reliability is implemented? It's got to take some more time. It's got to take some more bandwidth. It's got to use some. You've got to send extra information to get this to work. UDP, you don't have to do that. So really, UDP is about being a lean, mean protocol.
More efficient.
It's very efficient, and if you need any of this stuff, like reliability or flow control or congestion control, you could implement it yourself at the application layer. And then use UDP as a very lean, mean vehicle to get the packets there. Does that make sense? So it has uses. It kind of gives you a lot more control over the trade-offs you want to make. Whereas TCP, it's going to do a bunch of work for you and reliably get the data there, but you're going to have to pay the price in terms of speed. Okay. As we think about common internet applications and these properties of TCP and UDP that we just looked at, what transport layer do you think each of these protocols would be implemented in? So email, which is implemented in SMTP, what transport layer would you use to implement email? TCP or UDP?
TCP.
Why?
It's reliable.
Because you care about reliability, right? What about remote access? That is, you're remotely logging into another computer. This is the Telnet protocol is one protocol that does this. SSH is another. What do you think? Is that a...
You need reliable, wouldn't it?
Speed's important, though.
Speed's important, but if you're dealing with a person isn't really that fast in terms of a person typing. Reliability is really important here, too, because you don't want to lose a character and type L instead of LS, right, to do a directory listing. That would be completely different. What about HTTP, the web? Is that UDP, TCP? Do we need reliability when we're downloading web pages? Yeah, we do. We don't want half a web page. We want the whole thing. We want it to be exactly correct. So HTTP is implemented in TCP. File transfer protocol. We're moving a file from one computer to another. TCP, UDP. TCP. Streaming multimedia. What about that? Now we're finally getting to a point where maybe we could use UDP, where we can lose some packets, and we really care about things being fast. Short delays and no wasted bandwidth. Same goes for telephony protocols where we may use UDP for that.